Hi everyone. Today our topic is searching a region in the plane. So essentially what we're going to do is we're going to be making a rectangle on a coordinate plane and talking about how movement within that rectangle can reflect movement in real life. So our objective today is that students will be able to interpret graphs with relevant location data by using intuition and prior knowledge, such as the distance formula, slope information, intersection information, etc. So we're going to take all of these tools that you used in Algebra 1 or in your pre-algebra work in middle school, and we're going to be applying it to location data, which I'll be showing you an example of today. One application of this type of work is using a coordinate plane to represent locations for 3D computer modeling, which is often used in developing animation for video games and 3D animated movies. So one of the really unique ways that Pixar first did their animation, which made it so exciting for Disney Pixar movies like Toy Story and Inside Out and Finding Nemo, when they were first coming back in the early 2000s. These movies approached animation in this really unique way, where all of their objects that exist on the screen, in the computer, they exist in this three-dimensional kind of space. So they can actually do camera angles like you would in real life. If you were shooting a live action movie, they can use some of those same techniques using this computer-generated situation. So can you think of one other instance where taking a physical location and graphing that location in some way would be useful for us? Just think of one example when we would do that and put that in this box here. Thanks for working on that. Now let's move on to our notes for today. Our first section here says, students in a robotics class must program a robot to move in an empty rectangular warehouse. The program specifies location at a given time, t seconds. The room is twice as long as it is wide. Locations are represented as points in a coordinate plane, with the southwest corner of the room deemed the origin, and the northeast coordinate being 2,000, 1,000 in feet, as shown in the diagram below. So basically what they're telling us is that this graph is like we are looking down through the ceiling onto the floor of a room. Okay. Now, one really important piece of information that they tell us here is that the room is twice as long as it is wide, and that's really represented by this coordinate point here, right? This corner is 2,000, 1,000. So that means that down here, we're at 2,000 on the x-axis, and up here, we're at 1,000 on the y-axis. It's really important for us to remember that the x-axis is horizontal and the y-axis is vertical. All right, so let's look at what information it gives us here. This first piece of information says, the first program written has the robot moving at a constant speed in a straight line. At time t equals 1 second, the robot is at position 30, 45. Now keep in mind that this is 2,000, 1,000, right? So this is humongous. So that means right about here, we're at 1,000, right? So 30 is going to be pretty close here, and 45 is going to be pretty close here. I'm going to estimate that that's where our first point is, at 30, 45. And our second point is at 50, 75. We're supposed to complete the exercises and answer the questions below to program the robot's motion. So we're starting at 30, 45, which is this point. I'm going to label that point A. And then we're ending at 50, 75. So 50, we're going to go over here, up a little bit more. 50, 75 is B. Now keep in mind that these 2 points are probably not exactly where they should be for this graph, right? They should be a lot closer to the origin, but that would be really difficult for us to see if I plotted it to scale. So we're just going to go with this for now, accepting that point A is at position 30, 45, and point B is at position 50, 75. So our goal, the questions we're going to answer at the end are these 3 questions here. At what location will the robot hit the wall? At what speed will the robot hit the wall? And at what time will the robot hit the wall? So if the robot is starting at A, and if it's traveling through point B, and if it keeps going, when, where, and how fast will that robot be going when it hits this wall up here? That's the question we're trying to answer. So I'm going to ask you to think about these things and pick 2 of them to write about. So the first one says, to determine how far the robot moves, I could ... To identify where the robot starts and ends, I could ... To explain the path of the robot, I could ... Or to find the speed of the robot, I could ... So what I'm asking you to do here is think about what you could do using math or using your drawing skills, or if you were physically in the room, what could you do to figure out how far the robot moves, where the robot starts and ends, the path of the robot, or the speed of the robot? Okay. I would like you to pick 2 of these to put in these boxes. So these are just ideas. I won't be grading them on whether they're right or wrong or anything like that. I just want you to think about 2 of these sentences and then finish those sentences here. Go ahead, pause this video and work on thinking about 2 of these sentences before you move on. Thanks for thinking about that. Let's move down to our general exercises. So this exercise here says, first, plot the points on a coordinate plane. So this is exactly what I did when we first started this question over here, right? Plotting point A and point B. And I said that these aren't really to scale. They're a little bit further away from the origin than they should be, but this is really the only way that I can show them on my screen to where it actually makes sense. Right? And now we could do the same thing over here, right? We could say this is point A, this is point B, there's the line segment in between them, right? I'm going to do a zoomed in version of that on an additional coordinate plane here so that we can really see what's happening between these 2 points. So point A, we know, is going to be at a specific coordinate, and point B is also at a specific coordinate. Let's refer back to our original question here briefly. So we said point A is at 30, 45, and point B is at 50, 75. So point A is at 30, 45, and point B is at 50, 75. So we want to keep these 2 points in mind. So on my y-axis, I know that my top of my y-axis has to be at 75. I'm going to split this into intervals of about 25 because I know 25 goes into 75. So I'm going to say here I'll be at 25 on the y-axis, here I'll be at 50, and then up at the top I'll be at 75. Now on the x-axis, it looks like I need to plot 30 and 50. So I'm going to plot in intervals of 10 on the x-axis. So here we'll have 10, 20, 30, 40, and 50. So really, we're still inside this box, right? We're still inside our original graph. Just what I'm doing is I'm zooming in on this part of our graph so that we can just see the part that we're worried about for right now. We're going to use this bigger graph later, but if I start with this smaller one, it might help me with my first couple of questions. So to plot point A, 30, 45, this is always the x, then the y-axis, x and y. So point A will be at 30, 45 is almost 50, right? So here's point A. Now point B is going to be at 50, 75. It's up here in the corner. Here's point B. And number 2 says draw the segment connecting the points. So that segment that connects those 2 points is just the straight line segment in between them. All right, so we're going to be using this idea, this graph that we just made, to answer the rest of the questions. I might need to refer back to this pretty often. So the other piece of information that we didn't really think about when we first read the question was, when are we at each point? So the idea here is that at time is 1 second, we're at point A, and when the time is 3 seconds, we're at point B. So this is really important because number 3 and 4 says how much did the x coordinate change in 2 seconds and how much did the y coordinate change in 2 seconds, right? So when the robot starts moving, after it's moved for 1 second, it's at point A, right? So 1 second in, it's at point A. And then 3 seconds in, it's at point B, right? So it's somewhere over here to start. And then it goes 1 second, it's on point A. 2 seconds, 3 seconds, it gets to point B. So it's traveling from point A to point B, and it's doing that between 1 second and 3 seconds. Now, in total, if I'm starting at 1 second and I'm ending at 3 seconds, that means that there's 2 seconds in between there, right? If I had a number line, I start at 0 seconds, right? 1 second, 2 seconds, 3 seconds. If this is where we start and this is where we end, we have 1, 2 seconds. So that means that the total amount of time in between point A and point B is 2 seconds. So when this question, number 3, asks us, how much did the x-coordinate change in 2 seconds? It's saying, how much did the x-coordinate change between point A and point B? How much did we change in the x direction? So if I look here, point A is at 30 in the x direction, and point B is at 50 in the x direction. So how much did I change to go from 30 to 50? I changed 20 units, right? In this case, we are measuring in feet. So how much did I change between A and B? Well, I changed 20 feet. And there are 2 different ways that we could represent that, right? The first way I already did. I could draw on my graph. I could say I started at 30, I ended at 50, the space in between that is 20. I could do that. The other way that I could do this is say 50 minus 30 is 20. That's how I get the difference. Remember that difference is the same as subtraction. Now I can do the same thing for my y-coordinate, right? I know that at A, I'm at 45. At B, I'm at 75. So then I just need to know what's the difference there. What's the space in between those 2 things? Well, that's 30 feet. And if I wanted to check my work, right, I could go 75, which is the y-coordinate of B, minus 45, which is the y-coordinate of A, and I get 30 feet, right? So this is 30 feet. That's how much my y-coordinate changed in 2 seconds. Now, number 5 is asking us, what is the ratio of change in y to the change of x? Now, we know that the word ratio is the same as saying fraction, right? There are other ways that we can write ratios, but typically in geometry, we've been writing ratios as fractions. Now, the ratio of change, that's the same as the rate of change, which is the same as slope. And we know that slope is the change in y over the change in x. M is usually the letter we use for slope. We might say m is equal to the change in y over the change in x. Now, the first one we want in our numerator is the change in y. We know that that is 30 feet. So this is going to be 30 over our change in x. The change in x was 20 feet, so 30 over 20. And if I simplify this fraction, I'm going to get 3 over 2. That simplification just comes from me dividing by 10 in the numerator and dividing by 10 in the denominator to get 3 over 2 from 30 over 20. Now this next question says, what is the equation of the line of motion, right? So as our robot is moving from A to B, what's the equation of that line? Is what this question is asking us. Now, we know that we usually write equations in the form y is equal to mx plus b. This is something that you did a lot when you were in Algebra 1. Now m, we already have our m, right? We know that m is 3 over 2. So the only other variable we need to figure out is our b. And there are lots of different ways to do this. This time, I'm going to use point-slope form. We use the equation y minus y1 is equal to mx minus x1. Now, in this formula, y1 and x1 are coordinates from one of our points on our line segment. So I'm going to use point A. And m is our slope. A was 30, 45. So I'm going to use 30, 45 as my x1, y1. So y minus 45 is equal to m is my slope. I found that up here. It's my 3 over 2. And then I know that in parentheses I have x minus x1, which in this case is 30. Now, if I do this math, the first thing I need to do is distribute my 3/2 into my parentheses. So I have y minus 45 is equal to, remember we're using the distribution property here, 3 over 2x. Then I need to do 3 over 2 times 30. If I put this into my calculator or if I do it by hand, I'll see that I'm going to take that 30, divide it by 2. That gives me 15. Multiply that by 3, I actually get 45. And to solve for y, to get y by itself, I want to add that 45 to both sides. And actually, something really great happens where we just get y is equal to 3 over 2x. And the 45s cancel each other out because negative 45 plus 45 is equal to 0. So we don't actually have to write the plus 0 part on the end. And that means that our final answer is y is equal to 3 over 2x. I'm going to erase part of this so that it's not taking up so much space and just write our final answer. So number 7 is taking us in a little bit of a different direction. This is asking us more about distance. So what is the distance between the points? How far are we traveling? Right? So number 7 is asking us what theorem we can use, and number 8 is asking us how far. So let's talk about number 7 first, and I'm initially going to just start by looking at my graph. When I look at my graph here, my graph is pretty cluttered right now. But if I just look at my 2 points, right, point A and point B, if I look at this line segment, how can I figure out how far that line segment is? That's what we're going to try to think about now. Now, the big thing here is that I could actually make this into a triangle, right? I can make this into a right triangle by seeing how far did I move in the x direction and how far did I move in the y direction. Now, how do we figure out the sides of a right triangle? What theorem do we use? This is something you guys should probably remember. We use the Pythagorean theorem, and hopefully you remember that pretty well. So the theorem we're going to use, since we can make this a right triangle, remember that the Pythagorean theorem only works with right triangles. We can use the Pythagorean theorem. And hopefully we remember that the Pythagorean theorem is a squared plus b squared is equal to c squared, where a and b are our legs of the triangle, the 2 shorter sides, and c is the hypotenuse, the longer side. So let's figure out how far did we travel, right? Let's use this theorem to figure out our distance. So our distance x is going to be one of our legs. Our distance y is going to be the other leg. And then the hypotenuse is what we want to find, right? So I'm going to leave that as c, just as it is in the Pythagorean theorem. And we've actually already figured out what x and y are, right? Because this leg that I labeled x is really how much did we change in the x direction, and we already figured out that that's 20. And this y is how far did we change in the y direction, and we already figured out that that's 30. So let's plug those into our formula, and we get 20 squared plus 30 squared is equal to c squared. Now, when I put this in my calculator, I'll get 420 times 20 plus 930 times 30 is equal to c squared. Now, if I add those two together, I get 1300 is equal to c squared. Now, is 1300 my answer? The really big thing we want to ask ourselves is, does 1300 make sense? And the answer is most definitely not, right? 1300 is way too big. So what we want to do is we want to make sure that we remember our last step, the one that everyone forgets. We want to take the square root of both sides to get rid of this square. And what that does for us is it gives us c is equal to 36.1. Okay, so we get 36.1 feet as how far we went between point A and point B. Okay. So now we have these goal questions, right? Those questions that I asked us to think about at the beginning. At what location will the robot hit the wall? At what speed will the robot hit the wall? And at what time will the robot hit the wall? So when we're thinking about these questions, we are going to take what we know and we're going to extend it past what we know to get some more information about how this robot is moving, right? And we're going to do that in our minds, right? We're going to be extending past the information we currently have, but we're also going to be doing that physically on the picture. So what we're doing is we're taking this line segment that we're starting with point A and point B, and we're going to extend that line segment until it hits the wall. And we're going to figure out where that location is, what time that will be at, and what speed we're going. So the first of those questions, the speed question, we can actually answer right now. And the reason that we can answer that is that we know we are going at a constant speed. And that means that the speed the robot is traveling between that 1 and 3 seconds is the same as the speed it's going to be traveling forever. So this is the first really important formula that might be new to you. And this formula is that distance is equal to speed times time. Okay, so sometimes we simplify this so that it looks like this, or you might also see this as speed is equal to distance over time. And to get that version of the formula, you just divide each side by time. You can use either version of the formula if you would like. But this is the idea that when you're traveling, the distance that you go is equal to the speed you're going times the amount of time that you're spending. And that makes a lot of sense, right? If you're traveling at 60 miles per hour and you do that for 1 hour, the distance you've gone is 60 miles. So this is a pretty intuitive formula if you really think about it. So we're going to use this in this situation. Now we know that the distance we went was 36.1 feet. We figured that out in question number 8. We also know that the time we've taken was 2 seconds. We talked about where this 2 seconds comes from when we talked about number 3 and number 4. And if you need to rewind to refresh that part, you might want to do that. All right, so we know that the time we spent was 2 seconds. We know the distance we traveled was 36.1. So if I use this version of my formula, I get my speed is equal to my distance, 36.1, divided by my time, which was 2 seconds. This top part is in feet. So how far am I traveling? Well, I'm traveling approximately 18 feet per second. And that's the answer for part B. Now, what location will the robot be at when we hit the wall? Going back to part A. This actually isn't that tough of a question if we think about the formula we came up with in number 6. What you should be noticing is that these 8 questions that we did initially, all of these pieces are helping us when it comes to solving our final goal questions. So number 6 gave us an equation for the line, right? It gave us y is equal to 3 over 2 x. This was the equation that we came up with for our line that included that line segment between point A and point B. Now, when we hit the wall, we don't know exactly where we'll be if we're going back and forth on x, right? We don't know exactly where we'll be on the x-axis, but we know that we will be at 1,000 on the y-axis. And we know that because the entire wall is at the same height, right? It's all at 1,000 on the y-axis. So all we have to figure out is x. We already know the y coordinate, right? We have this mystery x, but we know we'll be at 1,000 on y. So let's use that information to our advantage. And keeping in mind that we know the equation, we can plug in the y value that we know. You should already know how to do this from your work in Algebra 1. So y, we know, is going to be 1,000. And we know the rest of our formula, 3 over 2 x. Now, we don't know what x is, but to figure out what x is, all we have to do is multiply by the reciprocal of 3 over 2. So we're going to multiply each side by 2 over 3 to cancel out our 2 and cancel out our 3. So we multiply over here by 2 over 3. And we should end up with x is equal to, now if we take this and we put this into our calculator, we'll do 1,000 times 2, which gives us 2,000, divided by 3. And we get 666.6 repeating. So I'm going to round that to 666.7. feet for x. So what location will we hit the wall? Well, if we put this in the same coordinates that we were using before, we know that our x is 666.7, and we know that our y is 1,000, because that's where the wall is. So this is our final answer for part A. Now for part C. At what time will the robot hit the wall? So this is a really important question because we really need to know how far are we going, right? The equations that we have that deal with time are this distance equation, right? Distance is equal to speed times time. And this rearrangement of that equation, speed is equal to distance divided by time, right? So in both of these equations, they're essentially the same, but in each one we have distance, speed, and time. And right now we're asking for time, which means we need to know what the distance is, and we also need to know what the speed is. Now we already know the speed because the speed is constant. We know the speed will be 18 feet per second. Now we just need to be thinking about what the distance will be, right? Let's say that we're starting at point A. And then we're going to the 666.7, 1,000 location, right? So we know to figure out that distance, we're going to use the Pythagorean theorem, right? If we go back to our graph, we can think about this in a little bit of a bigger way, right? If I'm starting at point A, which is down here, and I'm figuring out what this distance is, so I can figure out what the time will be to get all the way to this point, well, I'm going to need to see how much did I change in my x direction, how much did I change in my y direction to get my 2 legs for the Pythagorean theorem. And we know that when we did this before, just between A and B, that involved us subtracting our points. So we're going to do that exact same thing again. I'm going to use point A for this. A was at 30:45, and at t is equal to 1 second. So if I want to figure out what t is equal to at point, I'm going to call this point C, which is 666.7, 1,000. This is the location where we touch the wall. What is our t value here? What's our time? Well, first we have to figure out our distance. So to figure out that distance, the first thing I do is subtract my y values. So I'm going to do 1,000 minus 45. And I'm also going to subtract my x values, which is 666.7 minus 30. For my y answer, 1,000 minus 45, I should get 955. For my x answer, 666.7 minus 30, I should get 636.7. So remember that when we used the Pythagorean theorem before, each of these numbers were our two distances for our legs. So if we think about our Pythagorean theorem, we have a squared plus b squared is equal to c squared. I'm going to use my first number as my a squared. Remember that a squared and b squared we can flip-flop because both of the sides are the legs. It doesn't matter which one goes where. So we have 955 squared plus 636.7 squared is equal to c squared. Ooh, we got some very big numbers, which was to be expected, right? 1,317,411.89 is equal to c squared. We know that is way too big, and that reminds us that we have to take the square root of both sides to get rid of that squared on our c. So we finally get c is equal to 1,147.8. So this is our distance, right? We have now found the distance between point A and C. And since we know the distance and we also know our speed, which is 18 feet per second, we can use our distance is equal to speed times time if we want to figure out what the time is. So our distance, we know, is 1,147.8. We know that our speed is 18 feet per second, and we want to figure out the time. So to figure out time using this equation, since the 18 and the t are multiplied, all we have to do is divide. And we get t is equal to 63.8. So that means that the time we end up with is 63.8. Now, if you wrote down 63.8, I would not blame you. But there is one last step that we have to do if we want to actually be accurate. This is the amount of time between point A and point C, if point C is where we hit the wall, right? But point A wasn't at 0 seconds. It was at 1 second. So we need to take this 1 where A is, and we need to add it to our 63.8 to get our time for C. So our actual time for C is going to be 64.8 seconds. Now that was a lot of work. I would highly recommend that as you are doing the practice problems, you come and you refer back to these parts of the videos where you might need some help. If you're getting tripped up on this stuff, you can refer to Khan Academy videos, or you can come to online coach class for some extra help. Good luck. I hope that it goes well for you. And remember, you can watch this video as many times as you need to really understand what's going on. Have a wonderful day.